Okay, so what we want to do in this video, we want to look at the elements of rational functions. Remember, a rational function is going to be a function where you have a polynomial in the numerator and a polynomial in the denominator. Polynomials typically are going to be written in standard form. What that means is I'm going to have the leading coefficient first. It's leading because it's got the highest exponent. And so I'll see that on the numerator and the denominator. Okay, so remember also with a polynomial, that highest exponent has to be positive. It cannot be a fraction. And so those are really the things that we're going to be looking at when we get into some of our elements. Okay, so the first element that we want to look at is the domain. The domain is going to set the denominator equal to 0. And once we solve it, we're going to write an interval where it does not include those values. So we set it equal to 0, and then we exclude those numbers from the domain. So if we look at this first example here, I'm going to set my denominator equal to 0. This one is already factored for us, so we can quickly go to our answer. Remember, once it's factored, I'm going to set each factor equal to 0. And then I can solve. So to finish solving this, I'd subtract a 3 here. Here I'm going to add my x to the other side. So now that we see what they're equal to, the domain actually says that I cannot be these values. So I'm going to exclude this by saying that I'm going to go from negative infinity to negative 3, union negative 3 to 4, union 4 to infinity, remembering that interval notation. So my second example here, it is not factored. So the first thing that I'm going to have to do is I'm going to have to set the denominator equal to 0 and factor. So we talked about ways that we can factor before. So I'm going to have to remember all of those ways to factor. So what I'm trying to do is factor this quadratic equation here. Once it is factored, then I'm going to set each factor equal to 0 and solve. So I've got 3x equals 1. So x is 1/3. And x is negative 2. Now remember, we're going to exclude these values from the domain. So I'm going to say negative infinity to negative 2, union negative 2 to 1/3, union 1/3 to infinity. And remember, with this interval notation, all you're doing is you're excluding those numbers and you're going basically thinking about a number line in number order. So in the first example, I excluded the negative 3 first because it came first in a number line, and then I excluded the 4 next. In this example, I'd exclude the negative 2 first and then the 1/3, thinking about a number line there. The next thing that we want to talk about when you look at a rational function is an asymptote. So an asymptote is just a line of discontinuity. It's basically a line in which the function is going to get really, really close to it. It's going to approach it all the way off to infinity or negative infinity, but it's actually never going to cross or touch this value. In a rational function, we actually have two asymptotes. We have a vertical and horizontal. So the second element of a rational function is going to be that vertical asymptote. Sometimes we call it a VA. All right. So to find this, if we have an equation and we want to find the vertical asymptote, what we're going to do is we're going to factor the numerator and the denominator. If there's any factors that are the same, say there's an x plus 7 in the numerator and an x plus 7 in the denominator, I'm going to cancel those factors off. So only if they are exactly the same, can I cancel those off? After I've done any kind of canceling, if there's anything to be done, then whatever is left over in the denominator, that I'm going to solve it and it will become our vertical asymptote. So let's look at an example. Let's say, for example, we have x over x squared minus 4. So I'm going to factor the numerator, which it already is, and factor the denominator. That's going to be difference of perfect square. So I'm going to get x plus 2 and x minus 2. So I notice that there is nothing to cancel. There's no factors that are the same in the numerator and the denominator. So what that means is I'm going to set the denominator. So I have two things in the denominator. I'm going to set that equal to 0 and solve them. And both of these will become a vertical asymptote. So if I solve that first one there, subtract the 2, I'm going to get a vertical asymptote at negative 2. And then if I solve our second one, I add that 2, I'm going to get a second vertical asymptote at positive 2. All right, so let's look at another example here. In the second example, we've got x squared minus 9 over x squared plus 4x minus 21. Again, I'm going to factor them first. So the top is a difference of perfect squares, so I'm going to have x plus 3, x minus 3. The denominator, I want to say, okay, well, what's going to multiply to negative 21 and add to 4? So I'm going to get x plus 7 and x minus 3. So now that I've factored the numerator and the denominator, I actually do have factors that will cancel here, because what I notice is that this x minus 3 and this x minus 3 are exactly the same. So I'm actually going to factor those, or excuse me, I'm going to cancel those factors off. So then I'd only be left with my x plus 3 over my x plus 7. That would be the factored form. Now I'm going to find anything in the denominator. So now I only have an x plus 7 in the denominator for me to solve. So move that 7. So I only have one vertical asymptote this time at negative 7 because the x minus 3 canceled. Even though it was originally in the denominator, meaning it's in the domain, right, which is what we just talked about, it's not going to be a vertical asymptote. It'll actually be a whole or removable discontinuity. We won't really look at those too much here, but it's not a vertical asymptote if it cancels off. Okay. Okay, so remember we said there were two asymptotes. There's a vertical asymptote, which is what we just did, and then we have a horizontal asymptote, which could also turn into what we call an oblique asymptote. And so we'll see that here in just a second. So a horizontal asymptote, unlike really doing math like what we did last time where we were factoring and canceling and solving, this is more of a comparison. So I don't need to do any factoring. I'm going to look at the original equation and I'm going to compare the highest exponents, so which should be our leading coefficients, right? Our leading terms. I'm going to compare the exponents. When we compare two numbers, we really have three options. One is bigger than the other. So if the top could be greater than, the top could be less than, the top could be equal to. Okay, so in those three scenarios, we'll come up with different types of asymptotes. So let's say that we compare these exponents, okay, the highest exponent in the numerator, the highest exponent in the denominator, and we find that the numerator is actually smaller than, so in this first case here, we've got the numerator being smaller than the denominator, the exponent. Remember, we're talking about the exponent. In that case, the horizontal asymptote is at y equals 0. There's no math. This is all kind of memorization of the three comparisons. Okay, so I'm not going to do any math. I just have to know when I see these two things getting compared, depending on which case that they are, will give me the answer. Okay. Our next scenario says that the two exponents are equal. So let's say that they are equal to each other. Then I'm going to take the leading coefficient. So remember, that's going to be the numbers in front of our variable. Now, the third scenario would be that the numerator exponent is greater than the denominator exponent. In this case, we have no horizontal asymptote. Instead, it now becomes what we have called an oblique asymptote. So it's no longer going to be a horizontal line. It can be one of multiple things. It could be a line that is slanted. So some books will call that a slant asymptote. Or it could be some sort of any other function, any power function. So it could be a quadratic. It could be a cubic. It could be anything else. So we call those an oblique asymptote. We are only going to look at two types of oblique asymptotes. So when we compare them, if the numerator is one more than the denominator, then we're going to use our equation y equals ax plus b. And it's literally still coming from the lead coefficient up there. If the numerator is two numbers or two values bigger than the denominator, then we're going to have what we call a power function. So we're going to have that same a divided by b, still getting everything from those same leading coefficients. And then we're going to have x raised to the n minus m. So we're going to look at those and kind of see what's happening, okay? So let's try an example here. Before we do this, let me just remind you, all we want to do in these kind of cases here is we want to memorize our cases here. We want to memorize these. Okay. So let's look at these examples. So in the first example here, remember all we care about is that leading coefficient in those exponents. So I'm going to kind of circle these here. All right. I don't care about the negative x, the positive 2, the negative, I don't care about those, right? Remember, we're only comparing our highest exponents. So I see that the highest exponent here, 2, is equal to 2. So that's going to be my second case there. So my horizontal asymptote is going to be y equals a over b. Then I can reduce that. So y would equal 2. I just wanted to show you the 8 divided by 4 so you could go back and remember where we got it. All right, so let's look at this next example. Again, I focus only on those lead coefficients and that leading term there. So I compare. I've got 4, which is greater than 3. So this leads me to say, okay, well, there is no horizontal asymptote. Instead, I'm going to have a oblique asymptote. So now I have to ask myself, okay, is 4 one more number than 3? 2 more numbers than 3? So 4 is actually one more number than 3. So that means that my horizontal asymptote is none. My oblique asymptote is y equals a x plus b. And I got a 1 because remember, when there's no number there, I'm going to pull a 1 there. Okay. Let's look at another example. Again, I care about those the leading term and the leading coefficient there. So I'm going to compare. 3 compares to 5. 3 is actually less than 5, which means that my horizontal asymptote is at 0. All right, our last one here. Compare those leading terms, leading coefficient there. I've got 5, which is greater than 3. So again, that means there's no horizontal asymptote. So therefore, there's an oblique asymptote. So I got to ask myself, okay, is 5 one more number or 2 more numbers than 3? And it's 2. So that means I'm going to have y equals a divided by b. Remember, there's a 1 there. So it'd be 2 over 1. I'll reduce it in a minute. I just want you to see what's happening. So it's going to be 2 over 1 x to the 5 minus 3. Okay. So let's look what that answer will actually be. The answer actually is going to end up being y equals 2x squared. And I just wanted to show you where I'm getting all of those elements from. So again, horizontal asymptote, we are merely memorizing those 4 cases. and being able to recognize which scenario that we are in. All right, here we are to our last element, and it's talking about intercepts. Now, we've seen intercepts before. When we look at an intercept, we want to look at an x-intercept and a y-intercept. The x-intercept is where the graph is going to cross the x-axis. The way I'm going to find this in an equation is I'm going to plug in 0 for y and solve for x. Okay. Y-intercept is where it's going to cross the y-axis, but to solve it, I'm going to plug in 0 for x and solve for y. Now, we've done these before, so hopefully this is a little bit of a review. So let's go ahead and start here. Let's find our x-intercept in this first equation. So remember, in an x-intercept, I'm going to plug in a 0 for the y. I'm going to solve it for x. Now, first thing I see here is, oh gosh, I got a fraction. I do not like fractions. So I want to multiply by that denominator to get rid of that fraction. I'm going to do that to both sides here. Zero times anything is still 0. Those two are going to cancel, so I have x plus 3 equals 0. Oh, much easier problem to solve now. So now I'm going to subtract that 3, so I get an x-intercept of -3. And I can write that as -3, 0. 0 because that's what I plugged in. Okay. So let's talk about the y-intercept. To get the y-intercept, I'm going to plug in 0 for x and solve for y. So 0 plus 3 over 0 squared minus 1. My zeros go away, so I get 3 over a -1. So my y-intercept is -3. I could write that as 0, -3, because that 0 is what I plugged in for the x. Right? So look at this last example here. X-intercept. I'm going to plug in a 0 for the y. Okay. Same thing. I've got a fraction. I need to multiply by that denominator. It's going to be the step every single time. I want to get rid of that denominator first. I multiply by it. If it's equal to 0, it's going to go away. Okay. So now I'm going to solve my equation. I can solve this one of two ways. I could factor this, x plus 2x minus 2, because it's difference of perfect squares. Or I could go ahead and solve it with addition and then square root, remembering that I get a plus and a minus when I take the square root. So the square root of 4 is not just 2, but it's plus and minus 2. So really I have an x-intercept at 2, 0, and an x-intercept at -2, 0. Yeah, that's the main thing people will forget when you're solving, and you're just going to, oh, let me just take the square root, and then you forget it's plus and minus. So don't forget that. All right, so now let's look at our y-intercept. Our y-intercept, I'm going to plug in a 0 for the x and solve for y. So the zeros go away. -4 over 5. It is okay to have a fraction. I started with a fraction as my equation, so I might end up with a fraction as my answer. That's perfectly fine. So I can write, you can make it a decimal if you want, it's up to you. Okay, so all I want to do here is I want to review all of the steps that we've done. We're going to put it all together and see if we can find all of the different elements. Okay, so the first thing that we want to find is our domain. So remember, our domain is going to set that denominator equal to 0. So I'm going to add that 1 to the other side. I'm going to take the cubed root of 1, so x is going to equal 1. Okay, but remember, with a domain, we say actually it cannot equal that number. So my domain is going to exclude, so it's going to go from -infinity to 1, union 1 to infinity. All right. So the next thing that we want to do is find that vertical asymptote. So I'm going to factor the top. Well, the top's already been factored. I'm going to factor the bottom. Can't really factor the bottom. So I'm going to set the denominator factor, because it's already done, equal to 0 and solve it. So I'm going to get that same x cubed equals 1. So x equals 1 is my vertical asymptote. Okay. Next thing I want to do is I want to find my horizontal asymptote or my oblique asymptote, whichever one it ends up being. So remember, I'm going to go over here and I'm going to compare my exponents. I notice that the numerator is smaller than the denominator, so that's going to be a horizontal asymptote at y equals 0. Again, I've just memorized those cases. No real math to that. Okay. The last thing I'm going to do is I'm going to find the intercept. So my x-intercept, I'm going to find by setting the equation. My y is 0. I'm going to multiply by that denominator. Those cancel. Divide by a 4, it's still 0. Take the square root of 0, it's still 0. So I've got an x-intercept at 0, 0. Then I can find my y-intercept. So my y-intercept, I'm going to say, y equals 4 times 0 squared. I'm just plugging in my 0 here. So I get 0 over negative 1, which is just 0. And I notice my y-intercept is at 0, 0. All right, so now we've taken all of the elements and solved it in one equation. Okay, let's try another example. Let's look at the second example here. So the first thing I'm going to kind of come up here writing. The first thing that we want to do is we want to find our domain. So I'm going to take that denominator, set it equal to 0. So I'm going to need to factor this. Now, some of y'all have gotten really good at factoring. Some of us maybe not. I don't know if you're using the table, kind of what you're doing here. So I'm going to use the table since that's how I showed you. I'd multiply 3 times 4, which gives me negative 12. Since it's a minus, I'm going to be subtracting them. So I want to multiply to get 12, and I'm going to get a negative, so I'm going to be subtracting them. So I'm going to have, let's see, 1 times 12, which when I subtract them gives me 11. Negative 12 and a positive 1 subtract to give me a negative 11, and that's what I want to use. So I'd have 3x squared plus 1x minus 12x minus 4. I'm going to group them. Again, if you have found that you like a different way of factoring better, that is perfectly fine. I'll group and see what I have in common, which is going to give me an x. So it's going to be 3x plus 1. Here I'm going to group them together. I have a negative 4 in common, which is going to give me 3x plus 1. I notice I have 3x plus 1 in common, which means I did it right. And then x minus 4. Okay, so now that it is factored, I would set each factor equal to 0 and solve it. Okay, then I have x minus 4 equals 0. So I have two numbers that actually, remember, I cannot be. So my domain is going to be negative infinity. It's a number line, so I want to start with the smaller one to negative 1/3, union negative 1/3 to 4, union 4 to infinity. So this one took a lot, kind of longer process to get the domain because the denominator had more to do with solving. It's just the nature of the beast. Whatever the equation calls for, that's how much work I'm going to have to do. Still, the process was the same. I set the denominator equal to 0. Okay. Now, one of the good things about this is that I have now already kind of factored my denominators. So when I get to my vertical asymptote in part B, I've already done part of the work. Okay, so let me kind of get this first one over here. All right, so I'm going to factor the numerator and the denominator. Well, the denominator has already been factored. 3x plus 1 and x minus 4. Okay, so I need to factor now the numerator. So I kind of do the same process with what I did up there. So when I factor that numerator, I'm going to come up with 2x plus 3 and x minus 4. Again, I can do the same process with the table or whatever you're used to factoring, but I do want to be able to factor them. So when I do this, now I notice, oh my gosh, I have something in common. So I can cross off those x minus 4s, which is going to leave me with 2x plus 3 over 3x plus 1. Now that I have kind of reduced this, I can see that my vertical asymptote is just going to be when 3x plus 1 equals 0. So I'm going to move that 1, divide by my 3. So I have a vertical asymptote at negative 1/3. Okay. So the next thing that I want to do, find that horizontal asymptote or slant. So I go and I compare those exponents here. When I compare those exponents, I notice that they are equal. So that means I'm going to have a horizontal asymptote at y equals 2 over 3. Again, I just memorized those kind of cases. No real math here. So the last thing that I'm going to do, come back down here, I'm going to find my x-intercept and my y-intercept. So my x-intercept, 0 equals 2x squared minus 5x minus 12. 3x squared minus 11x minus 4. So remember, I'm going to multiply by that denominator, which is going to make it go away. I've already factored this moments ago, so I'm just going to use the factors here that I got. Now remember, what happened with that x minus 4? It got crossed off. So it will get crossed off every single time I've done something. Okay, so sometimes what you might want to do when you're finding your x and your y-intercept is go back over here to the factored form that you had, and then you can just use that. It's up to you, whatever that you want to do. So I know that I'm going to now solve 2x plus 3 equal to 0. So I'm going to subtract that 3. And I'm going to get 0 equals 2x, divide by the 2. So x is going to equal 0. So I have an x-intercept at 0, 0. To get the y-intercept, I'm going to plug in a 0. So I'm going to end up with a negative 12 over a negative 4, which is going to give me 3. So I'd have 0, 3. Oh man, I just noticed that I did not solve that x-intercept right. Let me go back there. That was silly. I subtracted the 3, and then sorry about that. I subtracted the 3, and then I just didn't have it there. So it should be a negative 3 getting divided by 2. Sorry about that. That was crazy. I get a negative 3 over 2 as my x-intercept. Sorry. Okay. So I'm actually going to go to the next slide for this last example. All right, sorry, it was just getting pretty crazy on that page over there. So let's go. Last example. I want to find my domain. So I'm going to set that denominator equal to 0. I'm going to solve it. Remember, the domain means what I cannot be in that rational function. So it's going to be from negative infinity to negative 5/3 union negative 5/3 to infinity. Much easier than the last example, only because the denominator wasn't as difficult to solve. Okay, so it's not necessarily about, oh, the domain's always going to be a long problem or it's always going to be short. It's whatever the denominator says on solving. Okay, so next thing that I want to do is find that vertical asymptote. So to find the vertical asymptote, I'm going to factor the numerator and the denominator. So when I factor that numerator, the denominator is already factored. So I'm going to get 2x minus 1 and a 3x plus 5. Right? Again, however you want to go about factoring that. So now I notice that I have factors that are the same in the numerator and the denominator. And actually what I notice here is that there is nothing left. Excuse me. There's nothing left in the denominator. So that means I have no vertical asymptote. Even though I started with something in the denominator, it canceled off. So I have to make sure that when I find the vertical asymptote, I am factoring and canceling if I can. All right. The first example we did, there was nothing to cancel. So that was easy. Okay, it's just the denominator. But it's not always just the denominator. The domain is just the denominator. The vertical asymptote is after I factor and I cancel off whatever's left in the denominator. Okay, so be careful with that. The next thing I want to do is I want to compare my exponents here. So I notice that the numerator exponent is greater than the denominator exponent. So there's no horizontal asymptote, but there is going to be an oblique asymptote. So the oblique asymptote, I notice that 2 is greater by one number, right? So x squared is one value greater than just an x. So what that means is I'm going to have y equals my a x plus my b. All right, and again, just memorize those. Last thing I want to do is I want to find my intercept. So I'm going to get my x-intercept here. X-intercept, remember, I'm going to say 0 is equal to 6x squared plus 7x minus 5. Again, what we talked about last time, if I kind of want a shortcut, and what I typically like to do is I like to go back to this problem that I have already reduced. It's less work for me. I've already done the work one time. Why do it again? Right? So I'm actually going to solve this reduced form over here. Then I also don't have to think, oh, wait, did I cross off that factor? I don't remember, you know. So I just always go back to my reduced form. So I could get rid of the denominator. The denominator is just 1 this time, so it's not a big deal. Now I'm going to solve. Divide by that 2. So x is equal to 1/2. So I have an x-intercept at 1/2, comma 0. Now to find the y-intercept, I'm going to plug in my 0. Again, I could do this to the original or I could do this to my factored form here. So I'm just going to go back to my factored form to make it a bit easier. So I get -1/1. So y is equal to -1. So I have 0, -1. If I had gone back to the original, I would have gotten -5/5, which is still -1. So I'll get the same exact answers no matter what I go back to. If I go back to my factored form here, or if I go back to my original on those intercepts. All right. So now hopefully we can find all of the elements of a rational function.